Kanawa-Tsugi, mortised rabbeted oblique scarf joint, a splicing joint in which the two halves are identical. It is very strong and efficient, and is used for framing members such as posts, beams, and the base plate of the foundation. This joint is also assembled by sliding over each other the internal faces of the upper wood and lower wood, keeping the surfaces of the middle drops in close contact. To complete this splice, the upper wood is shifted away from the lower wood, along the longitudinal axis. Finally, a single draw pin is inserted between the middle drops, interlocking the front and back surfaces of the joint. When choosing the joinery, consider the environment of your construction site. This joint can only be assembled in an environment that allows horizontal movement because it is a joinery that connects horizontally. This joinery should be used in a flexible state, where the posts are long, and there are no braces, because if the post is short, it will not be possible to secure sufficient range of motion. The joint position from the reference line of the post to the end of the seam is about 150 mm. Sumitsuke, marking out. Akinori Abo, Master Carpenter, Koubokusa, born in 1956. I made this ink pot myself. By enlarging the inkwell, you don't have to replenish it with water as often. As you mark out the wood, the ink rapidly dries up. I made an ink pot with a large inkwell to prevent this, improving efficiency. I can draw thinner lines by making a sumisashi, a bamboo pen. Unless the bamboo pen is very fine and we accurately mark the measurements off from the carpenter's square, splicing numerous members together can impact the accuracy of the overall measurement. I do my best to ensure the overall length doesn't vary, even when joining several members together. This mark indicates the tip of the tenon, or the tenon. Here, this indented mark indicates that there will be a recess. Marking out is like playing the telephone game. It's simple if you mark out and cut the whole thing yourself. However, in reality, someone else will be doing the cutting. Your instructions must be clear to ensure that the person cutting the joint doesn't make mistakes. You must clearly communicate what needs doing and where. It becomes necessary to invent ways to display the information in a way that's easy to understand. It's just like the telephone game, right? This saw is very sturdy and thick. Or rather, its plate is very solid, so it doesn't get pulled by the wood grain and become crooked. Here, the sawn surface will be hand-planed later, so I've left the entire thickness of the marking line. Here, like this, you can see the full width of the marking line. I started using wide chisels because, in my opinion, simply because something is hand-carved doesn't mean you should work slowly. As carpenters who make things by hand, we still need to improve our performance and precision to increase work efficiency. A chisel of this width is rarely used, even in Japan. This genno, or Japanese hammer, weighs 200 monmei, 750 grams. During the Edo period, carpenters specializing in mortises used hammers with a weight of 200 monmei. I used this 200 monmei hammer to chisel joints, but few people still use it these days. Typically, a chisel of half this size, 1 sun 6bu, 48 mm, is used. By striking the chisel with a hammer, the chisel cuts into the wood like this. The pressure from the impact on the hammer causes the chisel to sink in, but if you double the chisel's width, you double its resistance. Hammers for regular chiseling typically weigh around 160 mon, 600 grams. However, this weight isn't suitable once you double the chisel's width. If you consider the way a chisel cuts into the wood when struck with a hammer, it becomes overwhelmingly clear that you should use a heavier hammer. When I mention that I use a wider chisel, everyone says, but a chisel that wide won't cut into the wood, will it? But naturally, it won't work unless you strike with a heavier hammer to suit. Here, I'm trying to leave a little extra wood around the middle. I'm not chiseling entirely plumb. I'm adjusting the cut to prevent chiseling too much wood from around the center. There's no turning back if you chisel off too much, but if you haven't taken off enough, you can slowly shave more off little by little. If you try to cut it in one go, it's faster, but it can also result in poor workmanship. Here, I aim to leave half the thickness of the marking line. It's a little thicker here. I plane with the blade protruding about 4 microns. Planing in this way naturally produces gaps, like so. If the adjoining surfaces are both neatly planed to leave half the thickness of their marking lines, ideally, the two half lines join to become one. You can see that there's still an excess of 1.5 millimeters, so we can shave off half of that using this chisel, approximately 0.75 millimeters. It's okay if it dips ever so slightly here, as the piece won't fit if the inside surfaces protrude. I reckon it's still around 0.3 of a millimeter too high. This area is still a little too high. This area is good. In this instance, I use a wide chisel to improve the accuracy of this surface. It looks good. If you use a regular width chisel, the cut surface tends to become uneven because the chisel will twist and turn. On the other hand, if you use this wide chisel, you can cut this width in 2 passes, and it'll also eliminate any surface unevenness. The same process is repeated here. If you repeat this 4 times, the surface will barely have any unevenness. Using this method produces exact results, plus it's quick. Even if the marking lines are set out very well, you can't produce a well-made product without good cutting techniques. If you don't have the skills to leave half the width of the marking lines, shave off too much, or cut poorly, you can't build exact, high-quality products. Placing confidence in the marking lines, I locate the cut, leaving half of the marking lines widths intact. You then make the two equal halves and join them together into a single member. After all these steps, the overall length still needs to be accurate. Carpenters have always paid careful attention to this as they make joints. I've provided some tolerance here. There's an old saying among carpenters called a shoddy lining. It's said that when the workmanship is poor, the concealed faces on the inside are, in fact, abutting against each other. So instead, the outer joins don't meet. We still have sayings that are derived from old proverbs. It's a little tight. It's gone through. Once the pieces are joined together, the marking lines must align. It cannot bend around the joint, it must be completely straight. If the mortised and tenoned components aren't made correctly, the spliced member may become crooked, forming a zigzag shape. We are mindful to ensure this doesn't happen. Though it wasn't needed today, you would usually also cut a mortise in the base plate of the foundation to insert a tenoned pillar. In this instance, I consider which areas should be made tight and how tight they can be to minimize any shifting as the wood settles. Each individual mortise and tenon joint between the foundation base plate and pillar will impact how a house shakes during an earthquake. We have expertise in preventing joints from becoming loose as the wood shrinks and settles, and we make the joints accordingly. Some areas need to be slightly tight, while others should be a standard fit. Each individual joint has unique requirements, which we pay close attention to. There's a small gap between the two adjoining surfaces here of about 1 mm. This is so that when the wood shrinks and warps, it doesn't form a space here, causing the member to bend. This is made of heartwood, so over time, it will bow. So, to minimize changes to the measurements caused by such deformations, we consider which areas have to be tight and so on. buildings are essentially three-dimensional cubes. However, to construct a building that can withstand the fourth dimension of time, you must ensure the strength of the building doesn't deteriorate as time passes. To achieve this, we need to provide tolerances where they are necessary, leave half of the marking lines intact where required, and work with extreme precision to ensure the spliced pieces become a single, solid member once assembled.